Um, Welcome, everyone, to the third presentation of the 2021 Fish Tales Lecture Series, presenting the science of Great Lakes fisheries. Tonight's presentation will be on using science to control sea lamprey in Lake Michigan by Jessica Barber. My name is Mark Holy, and I will moderate tonight's lecture. The Fish Tales Lecture Series is a collaboration between myself, a retired fish biologist, and Kagan Haringa, the naturalist and program director for Crossroads at Big Creek Learning Center and Nature Preserve. We welcome your comments about the lecture series and your suggestions that you might have for future topics. To provide that feedback, please send an email to fishtaleslecture@gmail.com as shown on the screen. Tonight, we are again pleased to partner with the Door County Library to utilize their expertise to host the online Zoom and Facebook Live presentations. I want to thank Laura Kayakan for her support with presenting this lecture tonight. You can access our previous two lectures by visiting online the Door County Library calendar on the dates of those two presentations, which was February 18th and March 4th, and click on the video link, or send an email to fishtaleslecture@gmail.com, and I will share the YouTube links with you. You will not want to miss our final lecture that will be on the Great Lakes Mass Marking Program for trout and salmon, Better Fisheries Through Better Science, on April 8th at 7 o'clock, presented by Charles Bronte from the U.S. Fish and Wildlife Service in Green Bay. For the courtesy of the speaker and audience, please make sure your microphone remains muted and turned off during the presentation. If you have questions, please enter them using the chat feature in the bottom toolbar on your screen. We will answer all questions asked at the end of the presentation. Finally, this lecture will be recorded and available on the Door County Library calendar and their YouTube page. The integrity of the Great Lakes fishing community was forever changed by the invasion of the sea lamprey after modifications to the Welland Canal in the early 1900s had created a pathway to the upper Great Lakes around the Niagara Falls. By 1937, lampreys were found in Lake Michigan, and their predation on native species caused the collapse of very valuable commercial and sport fisheries. By 1952, researchers began testing the efficacy of electrical barriers to block lamprey from entering streams to spawn. Hibbard's Creek and the Kewanee River, as shown in the picture on your screen, in Northeast Wisconsin, were two of the first experimental application of these electrical barriers. The science to keep sea lamprey numbers low enough to allow valuable fisheries to thrive has progressed significantly since 1952. And tonight, Jessica Barber will bring us up to date on the latest science of controlling sea lamprey in Lake Michigan. Jessica Barber is the field supervisor for the Sea Lamprey Control Program with the U.S. Fish and Wildlife Service at the Marquette Biological Station in Marquette, Michigan. She has worked for the service for over 20 years, with 18 of those years being with the Sea Lamprey Control Program. As field supervisor, Jess is responsible for delivery of the Sea Lamprey Control Program and managing the only two service offices in the United States dedicated to controlling sea lampreys across the Great Lakes region. She also worked at the Green Bay Fish and Wildlife Conservation Office for several years, focusing on lake trout assessment in Lake Michigan. Jess was born and raised in Reedsville, Wisconsin, and continues to proudly wear her cheese head as a Packer fan in the UP. She received a bachelor's degree and master's degree from the UW-Wisconsin Stevens Point and studied recruitment of wild and stock lake trout in Lake Superior. Outside of work, Jess spends a lot of time at football, hockey, and soccer games with her husband, watching their two sons play sports. And if there's any free time left, she also likes to spend time outdoors, camping, hiking, and biking with her family and friends. So Jess, please inform us on the latest science to control sea lamprey.
Thanks, Mark. Good evening, everyone. I'm so happy to be here tonight, albeit virtually, to share information on the Sea Lamprey Control Program. It's a critical component to fisheries rehabilitation in the Great Lakes. I do want to take a quick moment to thank our partners and those that live and recreate in the Great Lakes, because we couldn't do this without your help and support. So the U.S. Fish and Wildlife Service and the Department of Fisheries and Oceans, Canada, work together as agents of the Great Lakes Fishery Commission to control sea lampreys in the Great Lakes. Successful sea lamprey control has allowed for rehabilitation of a healthy Great Lakes ecosystem and economy that is now valued at more than $7 billion annually. Program success has only been possible through the annual operation of our sea lamprey control program, which has reduced sea lamprey populations by more than 90% from the pre-control abundance. Thanks to our hardworking control agents, sea lampreys kill less than 10 million pounds of Great Lakes fish annually, which is a fraction of the pre-control loss. So now let's go on a little tour of the sea lamprey control program so I can demonstrate how we use science every day. So I thought we could start with a quick overview of the sea lamprey life cycle. I think I can turn a pointer on here. There we go. So I'm going to start over here with the spawning adult. A spawning adult sea lamprey will migrate upstream in the spring to spawn, and then they die after spawning takes place. The fertilized eggs will hatch and emerge as larvae, then burrow into the substrate for 3 to 7 years, where they will live as filter feeders. Once they've reached a suitable size, about 100 to 120 millimeters, they will develop eyes and a sucker mouth and emerge from their burrows in the stream sediment, usually in the fall or early spring, and migrate downstream to the lake. Once in the lake, moving up around the life cycle here, they will immediately look for a host and begin feeding for 12 to 18 months. So moving back into the components of the program, I'm going to start first with a focus on the spawning adult phase of the sea lamprey. Each spring, we conduct a mark recapture survey on certain tributaries to each Great Lake to estimate the lake-wide abundance of adult sea lampreys. The lampreys are captured in nets or traps, typically set near barriers each spring from about March through June or July, depending on where the tributary is. A certain proportion of those lampreys that we catch are marked with a unique fin clip, and then we release them. By comparing the proportion of marked and unmarked animals in catches, we can then estimate the stream population of adults using the equation seen here. This is one of our bigger traps as well. During trapping, we try to focus on 3 things when we place the traps so that we can maximize our efficiency. We look at 1, the attraction to the trap, 2, getting the lampreys in the trap, and then 3rd, once they're in the trap, keeping them in the trap. Sea lamprey are attracted to flow, and they are very curious, poking around because they're highly motivated to migrate upstream in search of spawning grounds. So they will keep poking around and moving upstream as far as they can go until spawning is imminent. As the temperature rises, their condition decreases throughout the spawning season. Our barrier integrated traps are more efficient than nets that we would set in an open river because lamprey do congregate at barriers because they can't move upstream any farther than that. And then some trap designs that we have allow us to control the flow so we can work with that attraction flow that I was talking about a little earlier. We do have several locations that we trap sea lampreys around Lake Michigan. We do have 9 of those. We look for good geographic coverage around the lake where we see productive tributaries. You'll notice that we don't have any traps in this area of Lake Michigan because we don't have any producing tributaries in that area. So somebody should go knock on some wood somewhere, but we're good in that area for right now. But the other ones are located around the northern Lake Michigan and on the eastern shore. So we collect information at those 9 sites around Lake Michigan, and again, looking for good geographic coverage. And those mark recapture estimates that we collect at each of those locations are summed to create an index of adults in the lake. And then that index we use as a tool to gauge program success and evaluate treatment strategy. So it allows us just to get a quick snapshot of how we're doing. This graph is the result of all the trapping work done during the spring, and this represents the Lake Michigan Index of Adult Abundance. Spawning year is on the x-axis, and the index of adult sea lampreys is on the y-axis. This horizontal line right here indicates the target abundance of sea lampreys that we're shooting for. And the good news in Lake Michigan, as you can see, is that we have been less than target in Lake Michigan and have been holding steady for the last 5 years. So we're still in the adult spawning adult phase of the life cycle, but now we're going to switch gears from talking about assessment over to control via barriers. So our barrier program is responsible for operating and maintaining barriers around the Great Lakes. Within the barrier program, we have a network of structures that we have built to prevent sea lampreys from reaching spawning habitat. There are also hundreds of other existing structures that also serve purpose to block sea lampreys, even though that isn't why they were constructed. We can only treat so many streams per year, so we rely on barriers in the Great Lakes to help us protect over 200,000 miles of upstream habitat. We have a number of different types of physical barriers that we have deployed throughout the program. The low-head barrier is the primary tool that we use to block adult lampreys from reaching spawning habitat. The low-head barrier is the most effective barrier that we have because lampreys can jump, but they can't jump higher than 18 inches. So when we design a structure, we make sure that we don't ever lose an 18-inch drop between the barrier crest and the tailwater. The closer to the mouth that you can site a barrier, the better, because the goal is to reduce or eliminate stream miles that would require treatment. In recent years, the competing objectives of sea lamprey control and aquatic connectivity have resulted in a synergistic effort to investigate selective fish passage. Because as you know, when we put in barriers, we're not only blocking sea lamprey, we're blocking other fish species as well. So there's a lot of good stuff going on right now to look into how we can construct barriers but still pass desired fishes. So in addition to the fixed crest low-head barrier, we do have several other types of physical barriers that we use in the program. We have seasonal barriers, which are adjusted to be in place during the sea lamprey spawning run, allowing passage during other times of the year. So we'll go and right about this time of the year, we go and either put stop logs in, or this one is a lift gate. We go and raise the gate to pull the barrier up. And then after the spawning run, typically in July, August, we'll go and take those seasonal structures back down to allow fish passage. We also have a few velocity barriers in the program. What's nice about velocity barriers is that we don't have to build them as high and they reduce upstream impoundments, but we have yet to be fully, we haven't fully adopted those in the program yet because it does push us a little farther out on that risky end of the continuum. And then of course, there are a number of natural features around the Great Lakes that also serve as barriers. Recently, we've also been revisiting the use of non-physical barriers for the reasons I've mentioned earlier, flooding, impoundments, and fish passage. Non-physical barriers are designed to perform similarly, but do rely on different technologies and require much less infrastructure. They also allow for a more natural channel design and flow. Some examples of these include the portable electric barrier, light bubble sound curtains, and pheromone and alarm cues. Many of these types of barriers remain in the investigative stage. We also do engage in new barrier construction when it is feasible and supported by local agencies and landowners. Even though we're biologists by training, we also need to have a general understanding of how to read blueprints, stream hydrology, and geomorphology, surveys and map making, even going so far as welding and fabrication, animal behavior, hydroacoustics, and even negotiation skills to be successful in barrier construction. Have to go to a lot of public meetings and go and talk to stakeholders and landowners about the program, why it exists, and why it's important to them. So to gain support for things like barrier construction projects. We also need to stay on top of new technology to broaden our collaborative network to ensure that we advance the program. As far as barrier siting and design, after we have those initial conversations about whether it's feasible and whether we have support from stakeholders, landowners, and partner agencies, we need to go out and collect hydraulic and hydrologic information and then model that information so that you can site a barrier. Looking at how high a structure needs to be, look at the topography, the amount of water that would be impounded behind it, and the length of stream miles that we could block sea lampreys. So in cooperation then with local agencies and landowners, we'll choose a location that offers the best protection from lamprey invasion while also minimizing upstream flooding and public safety threats. I'll go through a couple of examples now within our barrier program. The first example comes from the Grand Rapids area. This is the 6th Street Dam in Grand Rapids. It currently protects about 1,400 miles of upstream habitat. And if this structure failed, it would devastate the Lake Michigan fishery. However, this dam is aging and the city is looking to redesign the barrier to be more fish and people friendly. The current 6th Street Dam is not a barrier design that the control program would have used, but it seems to work in this river. It has a curved crest. We call it an OG crest barrier. So it's not something that we would have designed to use in the program, but as I mentioned, it seems to work. So we actually tasked some engineers with figuring out why the 6th Street Dam does block lampreys. As they began looking at it, they determined that velocity must be the major component that is blocking sea lampreys. So even though we can't maintain that 18-inch drop that I talked about earlier, the velocities are prohibitive enough that lampreys can't swim past. Flooding is an issue in this location. So whatever we decide, whatever the city and the partner agencies decide to do, whether that's a rebuild of this structure or building something new elsewhere, we need to also consider the flooding issue. So we need to make sure that the barrier can be adjustable to accommodate any high flows. So this challenges the program certainly to put their trust in engineers to design a structure that will ultimately rely on velocity and adjustable barrier technology. Velocity barriers are something we're investigating because it does allow for additional design options that you can't get with a low head structure. The velocity studies that we've been doing have been mostly done in large flumes to test swimming capabilities, and the results have been used to help us design velocity barriers that don't require jumping to block animals. The graphs on this slide are just examples from the Grand River. We're currently trying to target the 4 millimeters per second over 10 meters with some substrate that minimizes attachment. So on this curve, this is a swimming endurance curve with the swim velocity on the x-axis, and we're looking to be down in this region with velocities because the sea lamprey can't swim very far when it's 4 meters per second. And then also we do use a substrate in some of those situations. It's a mesh panel basically that we use that prevents lampreys from being able to suction their way over a structure. And when designing structures like these, we actually rely pretty heavily on computer and physical models to evaluate the different design parameters. I have to tell you, these are really hard to decipher for a non-hydrologist or engineer. So we certainly have issues with interpreting models like this and even trusting the model outputs that they provide to us. Forces us to ask questions like, what sort of errors do these models have? What happens at the edges of these structures? Can lampreys squeak by? What happens if a tree comes down and wedges itself in the structure? Is that going to affect the velocities, and how will sea lampreys be able to navigate upstream around things like that? So Lots of work goes into these kinds of decisions. And as I mentioned earlier, the farther away from a low head barrier we get, the more risky the venture becomes. Another example of where velocity is being used in the barrier design is at the Harpers Field Barrier in Ohio. This was a rebuild project for an aging low head barrier that did protect and now still protects 1,200 stream miles upstream. Here we were able to maintain the same barrier crest elevation that had existed before, but the design has actually allowed us to increase the blocking ability using velocity during times of higher flow when the barrier would be inundated. And what was cool about this project is we had again tasked the engineers to come up with different ways to increase the efficiency of this barrier structure. And they actually developed these cool physical models in the lab to help confirm computer models, because for those of us who don't have a lot of training in engineering, it was really cool to see these physical models to back up what they were saying in the model outputs. So that was pretty cool. And unfortunately, in the barrier program, we also have to acknowledge that there are dam failures, with the most obvious example being the Manistee River Dam, which is on northern Lake Michigan. That structure began leaking shortly after 1990, and not long after that, sea lamprey abundance and lake trout wounding rose steadily. Currently, we're treating that upper watershed every 3 years at a cost of $750,000 per treatment. So we started this barrier rebuild project, I think almost 20 years ago. We're still sticking with it. We're planning to rebuild the dam and crossing our fingers that we'll be able to see some movement on this project in 2023. All right, talked a lot about spawning adults. How about if we move on to the larval phase of the sea lamprey? Our larval assessment unit in the sea lamprey control program is faced with a daunting task. They have to go out and try to find the sea lamprey larvae, which average about 75 millimeters or 3 inches in length, burrowed into the stream sediment. This is hard enough to do in just one stream, but there are thousands of Great Lakes tributaries. And those are indicated on the map on the slide. All the blue dots are all of the streams that have a history of having sea lamprey in them. Fortunately, only about a quarter of those tributaries have, of the thousands, fortunately only about a quarter of them have a history of sea lamprey infestation. But there's only so much time and resource available, and the larval units still survey around 350 streams and lentic areas each year. The objectives of the larval assessment unit are to detect new sea lamprey infestations, generate population estimates to help prioritize or rank streams for treatment, and guide and evaluate the effectiveness of lampricide treatments and barriers. As I mentioned, the larvae are small, they're difficult to find without specialized gear, and they can easily be confused with native lampreys. There are 4 species of lamprey that are native to the Great Lakes, and these include 2 parasitic species, the silver and the chestnut lamprey. And then there are also 2 non-parasitic species, the American brook and northern brook lamprey. The native lamprey species have co-evolved with the Great Lakes fishes and do not harmfully impact fish populations. The sea lamprey control program focuses exclusively on the invasive sea lamprey. Program field staff do undergo extensive training to accurately identify the various larval lampreys that they encounter. The fish ID skills and anatomy courses we took in college really come in handy here. As far as larval assessment methods, it takes special equipment to find those sneaky larvae. For areas that can be accessed with waders, we have staff that use a backpack electrofishing unit that has a unique design and special settings that will drive larvae out of their burrows and then immobilize them for collection. So that's this picture right here. There's the backpack electrofishing unit. Those are the paddles, and then they have little baskets on the end. So when the larvae come up out of the sediment, you got to be quick and scoop them with the paddle, and then be very adept at pulling that paddle up and then using the scoop to put it in in the bucket that's being held with the other hand. So you get pretty good at that over time, but when you first start, it's a little bit of a challenge. So then we also do surveys in areas that are too deep to wade, so we have to use other techniques to find the larvae. One of those tools is a deep water electrofishing boat. Using similar settings to the backpack electrofisher, the deep water unit is dropped near the bottom and then has a suction dredge to collect larvae that are immobilized by the electricity. So it's like a big vacuum, and bring them up to the surface for identification. Another tool for the deeper water is the use of a granular lampricide called balicide. Balicide is applied to the water and the granules slowly sink to the bottom where they will dissolve. Lamprey larvae in the vicinity of the granules become irritated, leaving their burrows, and then swim up to the surface where they can be collected. Larvae do prefer softer stream substrate like silty sand. Habitat surveys are conducted in all infested areas or where we think the larvae may live. Quantifying the available habitat within those infested areas is a critical variable used in estimating the total larval population in a stream. Habitat surveys in shallow water are conducted visually, but other methods are used in deeper areas, including hydroacoustic sensors and dredge sampling. Sorry, my computer got stuck for a second there. So in order to calculate the larval sea lamprey population in a stream, we use a relatively simple equation that we apply to that data that we collected in the field. I'm not going to go through that in depth here, but this example comes from Harlow Creek, which is actually on Lake Superior. But we will find the mean larval density in the electrofish plots, and then we'll multiply that by the total available habitat to generate a population estimate. So for Harlow Creek in this example, the population estimate was a little over 38,000 sea lampreys in that stream. Recall that larvae do live in the sediment for about 3 to 7 years, so we want to wait and treat just before a large pulse of larvae will leave the stream, essentially giving us more bang for the buck when we actually do apply chemical. So the program focuses its attention on that size class, which is about 100 millimeters or greater, and then prioritizes those streams for treatment according to a cost per kill method, treating those streams with the lowest cost per kill first. So in this example, 2,076 of those 38,000 larvae were big enough to transform and migrate out to the lake. So, and we know that it costs about $58,000 in lampricides and staffing to treat Harlow Creek. So we'll take that treatment cost and divide it by the number of large larvae that we expect to leave Harlow Creek. So for that example, it's $28.51 per large larvae killed. So when putting that information against all the other streams that we also did surveys on, Harlow Creek would have ranked at stream number 42 to be treated that year, which means that there were 41 other streams that would have been treated before that had a bigger bang for the buck as far as numbers we would kill per dollar. So depending on the resources available in that year, Harlow may or may not be treated depending on how much funding that we have. So, and if a stream that is infested ends up not being treated, it just doesn't make that cutoff, then we go back and resurvey it the next year and rank it again. As that larval population grows in abundance and length, that cost per kill will decrease, therefore increasing the likelihood that a treatment will occur. Sorry, I have to keep moving the faces around because it keeps covering my slides. Current larval survey methods are effective in many situations, but there are limitations, and of course, there's always room for improvement. So the program is currently exploring new survey methods, including the use of environmental DNA or eDNA. This involves analyzing water samples, looking for unique DNA signatures that are produced by organisms in the stream. This method has been used to detect other fish species such as Asian carp. eDNA could be a powerful tool for us to aid larval assessment crews in finding new sea lamprey infestations and determining infested area in streams and rivers, especially when larvae are low in abundance. As I said before, sometimes they can be really hard to find. If it's a low density stream, you really got to find just the right spot to come up with those lampreys and get them in the bucket. So hopefully this tool works out for us. We're just getting started on a couple of interesting research projects with eDNA. So sticking with the larval phase of the sea lamprey, now we'll move into the realm of lampricide control. As I mentioned earlier, there are over 5,000 tributaries of the Great Lakes, and around 500 of them have been infested with sea lampreys. Larval sea lamprey populations are controlled by applying federally registered lampricides to infested streams and lentic areas by our licensed staff. And they deploy specialized equipment and technologies to deliver those treatments. In the 1950s, after testing hundreds of compounds, the U.S. Fish and Wildlife Service identified a chemical compound that was effective in controlling sea lampreys without significantly impacting other species. So the way TFM works is that it disrupts energy metabolism in sea lampreys, which makes it hard for the lamprey to eliminate the chemical from its body, thereby suffocating it. TFM does come in two forms, as a liquid or a solid bar. When it is applied to streams, the water may have a yellow or green-like tint, and the lampricide will photodegrade as it moves through the system. The liquid form is most often used in a moving stream water treatment, and the TFM bars are applied to small tributaries during a mainstream treatment to prevent lampreys from seeking refuge in a tributary that's not being treated, as they try to swim away from the active chemical. Another compound that we use is called balicide. It's less costly and can boost the toxicity of TFM. So during some treatments, a liquid or powdered form of balicide is added to TFM to reduce the amount of TFM that we need during treatments. Additionally, we have a granular form of balicide that I did mention earlier because we also use it in larval assessment. And those are basically little grains of sand that are covered in this chemical called balicide, and it's a time-released coating. So, and that's applied to slow-moving or stationary waters where it sinks to the bottom. This enables control of larvae in areas where TFM can't be used and is referred to as a lentic treatment. About 200 Great Lakes tributaries and larval hotspots are regularly treated with lampricides to kill larvae before they have a chance to prey on fish. All right, so prior to a treatment, it's necessary to measure stream characteristics at various sites in a watershed to calculate the lampricide application rates using a variety of specialized equipment such as pH meters, dissolved oxygen meters, titrators, current meters, water samplers, and then laptops and tablets. So the relationship between pH and alkalinity is used to determine the toxicity values for lampricides in concentrations of parts per million. We apply the lowest concentration that will be effective at killing sea lampreys, and this is what we refer to as minimum lethal concentration. The chemical is delivered using specialized equipment such as peristaltic pumps, boats, and sprayers. The application rates of TFM liquid are continuously measured by technicians. I'm going to show a quick video that shows an actual granular balicide application using state-of-the-art spray boat that we have equipped with special operating system, where the granules are sprayed from the boat over the water surface, where again, as I mentioned, they settle to the bottom, dissolve, and then cause the lampreys to emerge from their burrows and die. So let's see if I can get this to go. Might have to turn the pointer off. So the balicide is coming out the back of the boat. Right. Not bad for a day's work, right? All right, so also within the control program, we have a risk assessment unit that works very closely with the Lamprey control unit. We've used bioassay trailers to conduct tests to determine the toxicity of lampricides to sea lampreys and non-target organisms. Stream water is pumped into the trailer and delivered to the individual tanks that have varying lampricide concentrations. And doing this stream side reduces the stress on the organisms and provides a more natural condition. The information collected during bioassays is used to make decisions about minimum lethal concentrations and timing of treatments. We have accumulated enough historic data on the toxicity of lampricides so that we only conduct this type of testing now when there is a concern by a partner agency for non-targets. And during all stream treatments, we monitor for non-target effects. So treating streams with lampricides is effective, but it can also be costly from both the financial and ecological perspective. Therefore, the development of alternate forms of control are necessary to carry the program forward. So we're always looking for ways to improve our work and expand our toolbox. In some cases, lampricides just aren't the correct solution. And there's also the time limiting factor or fund limiting factor. We just can't treat every stream every year. So speaking of not treating every stream every year, 2020 was a hard year for us, as I'm sure it was for everyone. COVID-19 prevented us from completing many of our program components. We were approved to work within a driving radius of the offices, no overnight travel. So you could go anywhere away from the office to do your field work as long as you could get back within an 8 to 10 hour day. And we were also limited to single riders and vehicles, which also made that work that much harder. And it got very tiring on our staff, but they're all very dedicated and did a great job pulling through the field season. So we did have 39 treatments that we did plan to do during 2020. That's all the diamonds and circles on the map. And then the circles are the large producers that we had planned to do. So of the 39 treatments that we planned to do, we did 11. Those are the yellow circles and the diamonds. And then we also were able to treat 7 of 11 large producers that we planned to treat. So again, we planned to do 39 treatments. We did 11, and then 7 of those were large producers. So we were still able to get out and get some work done. For 2021, we do have 25 treatments planned, and that does include the 4 large producers that we weren't able to treat during 2020. So now moving on to the juvenile and parasitic phase. I need to turn the laser pointer on. Sorry. Now we move on to the juvenile and parasitic phase of the sea lamprey. Unfortunately, this is also where it becomes more challenging to assess the life phase due to their mobile nature. We trap juvenile sea lamprey in the fall and spring during the outmigration as a mitigation technique when we can't treat or we need to capture lampreys needed for research. The conditions are super challenging because of the cold weather and the debris buildup. The gear freezes up and so do our staff. We generally use spike nets or screw traps to do this work. In a screw trap, the flow will turn the drum and then deposit the catch and debris into the folding cage. These techniques are not generally effective enough to be used for control or accurate assessment of the outmigrating population. We just use these techniques when we need the research animals or if we weren't able to treat a stream for some reason. That's a picture of the screw trap. We also collect parasitic juvenile sea lamprey from commercial fishers for use in research. There are so many gaps with the understanding of the juvenile life stage. Where do they go when they first leave a stream? What's their first meal? What's their preferred host? Is their first meal their preferred host? How often do they switch hosts? How many fish do they kill? How much do they move around the lake? What determines which stream they enter to spawn after they're done feeding? So many questions on this life phase, but it's really hard to get at those answers because they're really hard to follow around the lake. So moving into the information technology part of the program, as you can see, each unit within the program has its own set of complexities. The agents handle all of this with grace, exhibiting professionalism and commitment at every turn. So by now, maybe you're thinking, how in the world do they keep track of all of this information? Well, we have a sea lamprey control database that was created and managed in-house by our very own IT specialists. Field staff and the IT specialists have been working to develop and field test electronic data capture using rugged tablets and specially designed data forms in the hopes of moving to cloud-based technology in the next year or so. Electronic data collection can provide some time and work efficiencies in the field for our techs and biologists. Another cool thing is that data validation can be done real time as they're punching in data, which can provide better accuracy by preventing and alerting to errors as it's punched in. Formulas can be automated, eliminating the need to do math. And have you ever tried to read a coworker's writing and then either key punch it or paraphrase it to somebody else? It's difficult. So entering data directly into the tablet eliminates the need to key punch data, so also reducing errors and saving time. As far as data processing, this cuts down the time manually spent recording data and then having to key punch it into the database upon return to the office. Reports can be generated faster or in real time while out on the stream, can auto-populate appropriate figures and codes, and allows staff to look up specific details in the field that they might need to get the job done, and gives us a lot of flexibility to easily modify the data capture routines. And finally, we do have some mapping capabilities built into our software to provide easy access to mapped data through a variety of Esri products, including ArcGIS Pro. We can easily see, in this example, we can easily see what types of surveys have been completed and which sites are positive for sea lampreys. We are very excited to take the program to the next level with cloud-based data management and visualization. Getting into the home stretch here. So I want to talk a little bit about the Sea Lamprey Research side of the program. So the control agents are also heavily involved with the Great Lakes Fishery Commission research sections so that we can continue advancing the program. We've already touched on a few things throughout this presentation, like non-target mortality and eDNA assessment, but here I'll cover just a few more interesting things going on in the program. The USGS Upper Midwest Environmental Science Center is currently looking into alternate formulations for our TFM bars. As I mentioned earlier, we use a liquid form and then the bar form. So the bars, the old bar formulation had inconsistent dissolution rates and then melted into a gooey mess in the summer heat. So the new bars will be intended to last longer and maintain their shape. And we're also looking at a new pellet formulation of the bar as well. So hopefully that pans out. As far as trapping, we continue to develop several different trap types to determine what works best in a particular environment. A lot of research and technology development goes into building a better mouse trap. And in recent history, we've looked at using weirs, fish wheels, pheromones and attractants, and eel ladders. We've also looked at movement patterns prior to stream entry and during the upstream migration to exploit certain migrating behaviors. And then leading right into a new project of supplemental controls, the GLSC is embarking on a 10-year study to actually supplement our controls of barriers and lampricides with other control techniques. When I talk about it, I usually refer to it like throwing the kitchen sink at the control program, but in a measured approach. The study targets streams that we found to be difficult to treat or where there are other restrictions that prevent us from completing treatments. This multi-tiered approach includes techniques such as trapping, pheromones, and sterilization of male sea lampreys. We're currently in year 2 of this study, so stay tuned. that wraps up what I have for the control program. There is so much information on the Great Lakes Fishery Commission website. If you want to know more, you could probably get lost for hours on there. And then I just real quick want to thank all the staff that helped put this presentation together. They are the experts, and I apologize if I butchered anything that they gave me. So with that, I'll just try and answer any questions that you might have.
Okay, thank you very much, Jessica. That was a very thorough presentation. There is one, we do have one question here from Lisi Kitchell, and the question is, do you treat lamprey, larval lamprey leaving the stream? And if so, how and where?
We treat larval lamprey while they're still living in their burrows in the stream sediment. When they're leaving the stream, that's when we would use those mitigation techniques such as the screw traps and the fyke nets.
So are there any other questions? You can unmute, since we have no more on the chat right now, you can unmute if you have to, if you want to ask a question directly. So I have a question, Jessica, and it has to do with the impact of COVID on the treatment in 2020. I know that it's very complicated how when you treat streams and don't treat, and you rotate through streams so that the same streams don't get treated every year. But if you didn't hit your target in Lake Michigan, what's the possibility that we'll see an increase in sea lamprey mortality on fish in the coming year?
Very good question. It's like I get my magic 8-ball out. We were still able to complete a number of those treatments, and many of those were the large producers. I think we were already in a really good spot in the control program. It was getting harder and harder to find those larval lampreys that were of the 100 millimeter size. So I think we're a little bit ahead of the game moving into the 2020 season. So even though we didn't get a full treatment season, I still think we're going to be okay. I don't think we could sustain a second season like that, but I think we'll be okay with just one and maybe see a little blip. But I think we'll be right around the same area on that index as we were in the past couple of years. And our treatment crews are going to go out and hit it hard this summer. So,
as I recall in our pre-lecture conversations, Lake Michigan's lucky because it's located very closely to the two sea lamprey offices, so that when you can only make day trips, there's a higher percentage of the sites reached in Michigan than some of those other lakes that are further away. Is that correct?
That's correct. Lake Erie and Lake Ontario aren't seeing any treatments for 2 years. So,
okay, good. So what can you say about how well we're treating and where the barking rate is, or the mortality rate? Are we meeting the objectives, and how easy is that to occur?
Let me pull out my annual report. Right, we're doing, the metric that we look at, Mark, is the index of adult sea lampreys. And we're at that target. It's hard, hang on. There is a group, so we look at several metrics. We look at the wounding, we look at the index abundance, and sometimes those match up and sometimes they don't. We do have a group that's been assembled called Fish Lamp to try and figure out why those things don't match up. So there's a lot of good work going on in that. Most of it's ongoing yet, so I don't really have any results to share, but yeah. As far as, I don't know if I can even put this up there, but as far as like Lake Michigan goes for wounds per 100 lake trout, we've been less than target for 5 years. So that follows the index of adult abundance pretty closely in Lake Michigan, at least over the last 5 years. So hopefully that will also hold true as well.
And Lacey Kitchell has another question about how are the other Great Lakes doing? So how does Lake Michigan compare to the other lakes? Are they in worse shape, better shape?
Lake Michigan is good. Lake Superior was pretty good. Lake Superior saw a pretty huge drop last year. Hopefully we can maintain that drop moving into 2021. But Lake Huron was bouncing right around the target line. And Lake Erie is currently just below target. And we have had a love-hate relationship with the index in Lake Erie lately, because that was one that had bounced around quite a bit with a couple of really high years that we really couldn't explain, but that has come down. So that's good news too. We thought that maybe the St. Clair River might have been producing lampreys out to Lake Erie, but that population has come down there too. And then Lake Ontario also always usually bounces around that index line as well. So we're actually doing pretty good. And like I said, I think we're just in a really good place already. So if we do see a blip, hopefully it's just a small one.
So how much funding does it take to do the Sea Lamprey program every year?
The U.S. Fish and Wildlife Service gets a little under $10 million. And I just want to be sure before I say it out loud, the total program budget is usually about $30 million. So the Fish and Wildlife Service gets about a third of that.
So it's well, I just know that when I was working, certainly if sea lamprey gets a little bit out of control, that it means there's going to be a noticeable mortality on predator fish like trout and salmon, and your catch rates will be affected. So
yeah, for sure.
Yeah.
Yeah, we can't, we always talk about taking our foot off the gas. We can't do that.
Okay. Thank you very much. I don't see any more questions in chat. If anybody else has a question online, you can unmute yourself and ask it directly if you'd like.
Hi, Jessica. This is Rob Elliott.
Hi, Rob.
Hi there. And I guess I'll ask a couple questions that, not that I already know the answers, but there may be some people that are interested. Sea Lamprey control has been treating for a long time. And you talked about the toolbox and having to come up with new things to do all the time. How have the lamprey changed, or are there behaviors that are changing with them that are making it more difficult into the future? And then added with that, are there significant concerns with climate change and how the environment is changing that would make it easier or harder to deal with lamprey in the future?
Wow, that is a loaded question. I don't think that it's harder to find lampreys because there are less of them out there because we're doing such a great job. As far as them changing their behaviors, I don't think that we've seen a lot of that. I'm sure you're aware of the resistance work that's been going on. There was some concern that lampreys were in danger of developing a resistance to the lampricides, but that was found to not be the case in the work that Aaron Dunlop had done. So I know there's some other ongoing research with that. So I guess we'll just make sure that we keep our eyes on it. But for right now, it doesn't look like lampreys up till this point have developed any resistance to the chemicals that we use. But that also put an exclamation point on the fact that we need to make sure that we're looking for alternate ways of controlling sea lampreys in case we lose social license to keep doing what we're doing, or lampreys do develop any kind of resistance to that chemical. As far as climate change, yeah, that's a huge concern. I'm not sure what else to say about that other than, we're aware that the environmental variables can play a part on trap catches for sure, and how efficient we are in catching lampreys, depending on overwinter survival and surface temperatures and things like that. So there's lots of really cool research going on into all of those arenas.
Right. Yeah, thank you very much. Keep up the good work.
Thank you.
So Jess, I'm going to ask another question regarding non-target mortality when you do the treatments. What's a bad day, when you're doing it, and how long can some of those impacts last if there are any impacts on a stream?
That's a tough question too.
Sorry.
A
Well,
bad
I mean,
day-
let me ask it a different way. Is non-target mortality a very serious issue?
We take non-target mortality seriously, but we don't see it very often. Our treatment supervisors do a great job of leading those treatments and monitoring pHs and alkalinity and a number of other things that go into planning those treatments to make sure that we're not doing anything that would cause a significant non-target mortality. Do we see some mortality? Sure, but nothing. Rarely do we see anything that's, I'll call like a reportable incident. So
it's not like, especially if you only treat a stream once every 2, 3, 4 years, it's not like you're wiping out all the mayflies in the stream or something like that, correct?
right. Yep.
Yeah.
Yeah, and typically, I mean, something has to go wrong in a treatment to see, a significant mortality like that. I mean, obviously, when we're treating for lampreys, we're also killing the native lampreys, but there's the upstream populations that exist and they've been shown to be able to repopulate. So that hasn't been a concern either. Okay. It's your chance to ask another question, someone, if you want to unmute yourself and ask it. There's no more questions in the chat. So hearing none, I want to thank you very much, Jess. You did a great job, and I appreciate you taking the time to help us out on Fishtails lecture series. Not a problem, anytime.
Great, thank you. For the rest of you, don't forget April 8th. It's the mass marking program. Hope to see you then, and thank you for joining.